Hi, this is Marc Roth, and this is Mathematics for Social Justice. Today we're going to be looking at bowling pin puzzles, which is a topic I use in my algebra classes, and it's also something I've presented in math circles. I'm going to start by introducing mod 10. So if we have a clock with 10 numbers on it, we can also number counterclockwise with negative numbers. It's not necessary, but I like to write mod 10 inside. So if I were to add, say, 6 and 7, instead of writing 13 on this clock, I would start at 7, then go 6 spaces clockwise. 1, 2, 3, 4, 5, 6. And I would land on 3. So it's like adding 6 and 7 and getting 13, putting down the 3 and then forgetting about the 1. One interesting thing about this clock is that 5 and negative 5 are equal to each other. So I introduced the puzzle like this. The person solving the puzzle has to come up with a bottom row of 4 numbers and then add mod 10 in a Pascal triangle-like way so that every digit 0 through 9 is used with no repeats. So for example, if you start with 1, 5, 7, 9, 7 and 9 is 16, you only write down the 6 of 16. Then you get 12, you only write 2, 6, 8, 8, and 16 is 6. So this is not a solution, we got repeats. But it's an attempt. And then I just let the students try to solve this, and most of them start at the bottom. And eventually they realize that 0 causes a repeat. So the first shortcut is to realize that 0 has to go at the top. So at this point, we could introduce algebra. I didn't come up with this idea. It was the idea of the puzzle editor of the IBM Research Ponder This online, I guess you could call it a column. But anyway, I had submitted this problem to IBM Research Ponder This in, I believe it was September of 1999. And the puzzle editor wrote the solution using algebra. So we can put a C here, a B here, and an A here. I believe the puzzle editor had A, B, C, and D. So one improvement is to start with only 3 letters on the side and have 0 at the top. So then we can go ahead and solve the puzzle the following way. Put negative C here. C and negative C cancel to give you 0. Now, one nice thing about doing this in the classroom is the students can tell you the different algebraic expressions, and I have them do it in alphabetical order. So they would write the negative B before the C, because B and negative B cancel, and then C survives. So then I would call on another student. For this one, it would be B to cancel the negative B, and then it would be minus 2C, because C minus 2C is negative C. So they can go from C to negative C. To do that, they have to go backwards C and go backwards C again. So it's negative 2C. So next, we cancel the A, and then we add the B. Then we go from negative A, we have to cancel the negative A with A, and we have to go from B to negative B. So that's negative 2B, and then we add a C. And finally, we cancel the A with negative A. And then we go from negative 2B to B, which is 3B. And then go from C to negative 2C, which is minus 3C. You can ask the students to individually give you you can call in several students to help you with each individual rectangle. So then the next thing is all these numbers, if you were to add them, would add up to the numbers 0 through 9. If you add up all the numbers 0 through 9, you get 45. But on the mod 10 clock, that's just equal to 5. So if you add all this up, it's going to be equal to anything that ends in 5. And one nice thing about adding is you get to cancel things. So we can cancel C and negative C, B and negative B, A and negative A and negative A. Now we can cancel this C and this C with negative 2C. And we can cancel this B and this B with negative 2B. And finally, we just have 3B minus 3C. And that's equal to anything that ends in 5. But since I want to divide through by 3, I'll use 15. Then when you divide through by 3, that cancels, and B minus C is equal to 5. So I want to continue and find what C is equal to. So if I just add C to both sides, that cancels. So C plus 5 equals B. And I can subtract 5 from both sides. That cancels. So C equals B minus 5. But if you remember on the clock, negative 5 equals positive 5. So I can change the minus 5 to plus 5. And then we get what I call a big result. I usually make a big deal out of this and write big result. Especially if the students are young. I said, oh, we found a big result. So we just learned we can replace this C with B plus 5. So that makes this negative B plus 5. And that makes this 5. And that makes this negative B. Okay, so at this point, we can take a little detour. Instead of finishing the problem right now, let's go back to mod 6. So for mod 6, we use a different clock. So I got this idea from a teaching partner named Jessica Delgado. When you do the problem mod 6, we can try another shortcut. Once again, 0 has to go at the top because anywhere else it would cause a repeat. And then we can try 2 numbers here. One has to be the partner of the other in the following sense. When you add mod 6, 1 plus 5 are partners because they make 0. Their formal name is 1 is the additive inverse of the other. And you also have 2 and 4 are partners. And 3 is its own partner. Or we can say its own additive inverse. And 0 is its own partner. When I have 2 different numbers, I can call that a partner pair. So there's 2 partner pairs, and 1 partner pair goes here. It can either be 2, 4, or 1, 5. Suppose I go ahead and try 1, 5. Now where do I put the other partner pair? I can't put it here and here because that's not 0. I can't put them here and here because that's not 0. So the partner pair has to be here and here, which means 3 has to go here. So then 3 plus 4 is 7, but on the clock it's 1. So 3 plus 4 more is 1. It makes this 2. So this is a solution mod 6. But the main idea here is we didn't use algebra. We didn't need to, but we used these partner pairs. Okay, so now we're returning back to the mod 10 problem. So I like to joke around. It's an old catch-22 joke. Is it true that what's fair is fair? Is it true that what's right is right? Okay, if you don't agree with that, you should at least agree that b plus 5 is b plus 5. So we're going to put a 5 here, and this has to be negative b. So at this point, we want to know, this is A, where is its partner pair? Well, these two are partner pairs, and these two are partner pairs. So how many partner pairs are there when you're working mod 10? Well, we have 1 and 9, 2 and 8, 3 and 7, and 4 and 6. Okay, now 5 is its own partner, and 0 is its own partner when you're making 0. So to use the formal language, 0 is the additive identity, and 1 and 9, they're each the additive inverse of each other. So, so this is A. We want to know it's not 5 and it's not 0, so it does have a partner. But these two are partners of each other, and these two are partners of each other. So down here, we have to have 2 more partner pairs. So where is A's partner? Okay, it's not its own partner, so this, or this has to be A's partner. Well, this can't be A's partner because this is not 0. Could this be A's partner? The answer is no again, because if you have a partner pair here and here, the last partner pair would be here and here, and that's not 0. So the only place for the partner of A is here, and that's negative A. So at this point, we can actually start over. We don't need this anymore. So negative A plus something is 5. That's going to be A, which cancels negative A, plus 5. And we already figured out this is going to be the partner of this. So that's going to be negative A plus 5. So remember, 5 and 5 cancel because 5 and 5 is 10, which is equal to 0 mod 10. So then we can just add from there. A plus 5 is 2A plus 5. And here we're going to get negative 2A plus 5. And here we're going to get 5 and 5 canceling, so we're going to get negative 2A, which makes this 2A. Now we have the template for possible solutions. So just because the algebra worked out doesn't mean we're going to get a solution, though, but we can try. So we're going to let A be a number. Why don't we start with 1? So when A is 1, this is 6 because it's 1 plus 5. This is negative 1, so it's 9. And this is negative 1 plus 5, so it's 4. And then you just add from there and see if you get a solution. And we do. So it turns out you can put any number in for A except for 5 and 0, and you'll get a solution. But if you can actually take this one and flip it, you get the mirror image. So having an odd here will give you an even here, and that will always be the case. So if you can just try putting the odds here, you'll get an even here. So you're going to get 4 pairs that are where each pair has a image and its mirror image. So at this point, we can just put down the first one. I actually have this one memorized because if you look at the first 2 digits, it's 4 squared, and then 3 squared, and then 2 squared. So I have this one memorized. And then so from here, I get this one. And I also get another one. And I get another one. So then I ask my students, what did I do to the top one to give me the other three? It's like, what did I do to this, for example, to take me to here? Now, you can figure out different ways to do that. For example, you could just say, well, you add 2, and you add 2, and then you subtract 2, and you subtract 2. That's a good observation, but that's not how I did it. Or you might say, well, let's see, just try a number, and then do its mirror image, and then make 15, because we know that's 5. And then find the partner pair of 8 and put it here. So there's different ways to do it, but that's not how I did it. So I keep the students guessing for a while, and usually somebody figures out that the way I did it is with multiplication. It's multiplication mod 10. 3 times 1 is 3. 3 times 6 is 18. I only write down the 8 of 18. 3 times 9 is 27. 3 times 4 is 12. So I multiply by 3. And then I multiply by 7. 7 times 1 is 7. 7 times 6 is 42. 7 times 9 is 63. 7 times 4 is 28. I'm only putting down the ones column numbers. And then I times by 9. So after 7 and then 9. 9 times 1 is 9. 9 times 6 is 54. Just write the 4. 9 times 9 is 81. Just write the 1. And 9 times 4 is 36. Just write the 6. And of course, if you times by 1, you get the same thing back. So what I've done is I've written the fractions that have 10 as the denominator, and the numerator is 10 or less. And I'm going to circle the fractions that can't be reduced. So if we look at the numerators, these numbers are 1, 3, 7, and 9. And 3, 7, and 9 we used previously, but these are the numbers that are less than 10 that are relatively prime to 10. So this word relatively prime is important. There's a way to actually compute the numbers that are less than 10, relatively prime to 10. What you do is you take 10 and make a factor tree. And these are both prime. So these are the prime divisors of 10. There's a formula called the Euler phi function. So phi of 10 is equal to 10 times 1 minus 1 over 1 prime factor times 1 minus 1 over the other prime factor. So that's going to be 10 times a half times 4/5, which is 5 times 4/5. And that the 5's cancel and you get 4. So phi of 10 equals 4, which means there's 4 numbers less than 10 that are relatively prime to 10. Okay, so now we're going to do a second puzzle. This time, instead of adding mod 10, we're going to multiply mod 11. So we'll look at the mod 11 clock first. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And backwards it's -1, -2. In this puzzle, 1 has to be at the top because it's the multiplicative identity. So 1 anywhere else will cause repeats. So again, we could start with C, B, and A. So C times what will give you 1? It'll be 1 over C. And then B times what will give you C. So we're going to have to cancel that B, and we want the C to survive. Then here, C over B times what gives you 1 over C? Well, you're going to want a B up here to cancel this B, and we want 2 C's down here. So 1 cancels and 1 survives. But you don't write 2C, you write C squared. So then C cancels C and 1 C survives. Then here we're going to have an A down below to cancel the A, and the B survives. And then here we're going to need 2 B's down below, so it'll be B squared. And we have to cancel the A, and the C has to survive. And the last one's going to be, we need to cancel the C and have 2 more C's survive, so that's going to be C cubed. Then we need the A to survive, we need to cancel the A actually. And then we're going to have to cancel these 2 B's and have a B survive, so that's going to be B cubed. So now we're going to talk about partner pairs again, but this time we'll be looking for multiplicative inverses. So when you're working model 11, 2 times 6 equals 1. Because when you're working model 11, every time you multiply, you subtract the biggest multiple of 11 that you can. So you're always looking to subtract one of these numbers. So 2 times 6 is 12, take away 11 is 1. And 3 times 4 is 12, take away 11 is 1. 5 times 9 is 1 because it's 45 minus 44 is 1. And 7 times 8 is 1. Take away 55 from 56 gives you 1. Finally, we have 10 being its own partner. 10 times 10 is 100. Take away 99 is 1. And 1 is its own partner. So we can say these are the partner pairs. So if you times all the numbers, 1 through 10, you're going to get 1. Well, if you write this out, okay, you can cancel 2 and 6 because they make 1. 3 times 4 is 1. 5 times 9 is 1. And 7 times 8 is 1. So when you times all these numbers, you get 10. So if we were to multiply all this, things would cancel, but we would end up with 10. So we can cancel C and C, B and B, A and A and A. We can cancel these 2 B's with B squared. And we can cancel these 2 C's with C squared. So we're left with B cubed over C cubed. And we want all that to equal 10. Because when we times everything, we get 10. And remember, 10 is equal to negative 1 on the model 11 clock. So let's work with negative 1. So what could this be? It could be B over C could be negative 1 because negative 1 to the third power would be negative 1. So if you try all the other possibilities, negative 1 is the only number that you can cube that will give you negative 1. So we can write this down as, again, B over C equals negative 1. So we can times through by C and get B equals negative C, or C equals negative B. And again, that's a big result. Okay, so once we get this big result, we replace c with negative b. And this is still b and a. Instead of having negative b, we can have 10b, because negative 1 equals 10 on the Model 11 clock. We can write 10b, and this would be 10 over b, because then the b's would cancel, and 10 times 10 is 100, take away 99 is 1. So then here we would have 10, because 10 times b is 10b. And then here, the 10 will survive. We have to cancel this b, and this box will be 1 over b. So it's interesting. If we times this, we get 1. If we times this, we get 1. So these are partner pairs in terms of timesing the pair of numbers and getting 1. Once we get this 10, we can actually start over. So in terms of the partner pairs, we had a partner pair here, a partner pair here. We need new partner pairs in making 1. So this can't be A's partner pair, because that's not 1. 1's up here. And this can't be A's partner pair, because that would force the fourth partner pair to be here, and that's not 1. So the only place for the partner of A would be here. So it's 1 over A. And these two would be multiplied together and give you 1. So now, let's work on this box. We need to cancel this A. So it's going to be 10A, I believe. The A's cancel and the 10 survives. And this would be the partner pair of this one, which would make that 10 over A. Because if you times this, the A's cancel, and 10 times 10 is 100, minus 99 is 1. So we just move up from there. 10A times A would be 10A squared. And here we would have 10 over A squared. Instead of writing 10 here, we might as well just write negative A squared. And this would be, times this, we're going to get 10 over A squared, which would be negative 1 over A squared. And then if we times this, we're going to get positive A squared, because this is actually equal to negative 1. Negative 1 times negative A squared is positive A squared, and this will be 1 over A squared. So now, if we want to find a solution, maybe we let this A be a number. Let's let it be 2. So in that case, we would have 2. 10 times 2 is 20. Take away 11 is 9. And 1 over 2 would be 1/2. Times by 6, and times by 6, you get 6 over 12 minus 11 is 6 over 1, which is 6. So that makes this 6. And the partner pair of 9 is 5, because 9 times 5 is 45. Take away 44 is 1. 2 times 9 is 18. Take away 11 is 7. We already know this is going to be 10. 6 times 5 is 30. Take away 22 is 8. 70 take away 66 is 4. 80 take away 77 is 3. And 4 times 3 is 12. Take away 11 is 1. So we have a solution. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. When we were doing that problem, it may have seemed like we were doing almost the same problem. There were so many structural similarities between finding a solution when you're adding mod 10 and multiplying mod 11. So we might suspect that adding mod 10 and multiplying mod 11 are isomorphic. Of course, we have to be careful. We're adding the numbers 0 through 9 mod 10, and we're multiplying the numbers 1 through 10 mod 11. So we're not using 0, only the numbers 1 through 10 mod 11. So it turns out there is an isomorphism, and it comes from something called a primitive root. And it turns out 11 has 4 primitive roots. Let me show you what that means. So if we take like a little vertical line and we start, say, with 2. 2 is one of the primitive roots of 11. And you go 2 times 2 is 4. 2 times 4 is 8. And 2 times 8 is 16. Then you subtract 11. So you get 5. 2 times 5 is 10. 2 times 10 is 20. Take away 11 is 9. 2 times 9 is 18. Take away 11 is 7. 2 times 7 is 14. Take away 11 is 3. 2 times 3 is 6. And 2 times 6 is 12. Take away 11 is 1. So notice we get all the numbers 1 through 10. We get 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so here we're multiplying mod 11. On this side, we're going to be adding mod 10. So we want a number to start with, and we add by that number. We get to all the numbers 0 through 9 without a repeat. So if we start with 1 and keep adding 1, we get 2, 3, 4, 5, 6, 7, 8, 9, and 0. So these two things have a similar structure. So if we take, over here we have the solution 1, 6, 9, 4. And it gave us these other numbers. What happens if we go the other direction? So if 1 becomes 2, 6 becomes 9, 9 becomes 6, and 4 becomes 5. So let's see if this works. 2 times 9 is 18, take away 11 is 7, 9 times 6 is 54, take away 44 is 10, 6 times 5 is 30, take away 22 is 8, 70 take away 66 is 4, 80 take away 77 is 3, and 12 take away 11 is 1. So we do get a solution. We get 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So these two solutions are identified with each other. And we can call this a function. When you have an input, output, input, output, input, output. And this function has a name. It's called the anti-log. Okay, so when you're going the other direction, it's called the log. So the log of 5 is 4. The anti-log of 4 is 5. And log stands for logarithm. So we're working with discrete logarithms. And this is actually a good way to teach logarithms. We wouldn't necessarily have to use 2. Here we could use other numbers that get you to the top. For example, 6, 7, or 8 could also go here. Let me do just one of those. We'll try 6. And again, this 6 is called a primitive root. It's a primitive root mod 11. So 6 times 6 is 36. Take away 33 is 3. 6 times 3 is 18. Take away 11 is 7. 6 times 7 is 42. Take away 33 is 9. 6 times 9 is 54. Take away 44 is 10. 6 times 10 is 60. Take away 55 is 5. 6 times 5 is 30, Take away 22 is 8. 6 times 8 is 48. Take away 44 is 4. 6 times 4 is 24. Take away 22 is 2. 6 times 2 is 12. Take away 11 is 1. So we ended up with all the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 with no repeats. Go back and look at the algebra that we used to solve these problems. We should be struck by something. 2a becomes a squared. So this 2 that was a coefficient becomes an exponent here. Here we're adding. and here we're multiplying. 2a becomes a squared. Here we're subtracting. Here we're finding a reciprocal, so we're dividing. It looks like adding here becomes multiplying here. Subtracting here becomes dividing here. Timesing by 2 here becomes finding the second power here. So this is suggestive of the laws of logarithms. So maybe in teaching, it's a good idea to teach discrete logarithms in a high school algebra class, because it just seems to be a very natural way to develop them that's maybe less confusing than when you do regular logarithms. So let's try a problem. Let's just make something up. Suppose we're doing 3 to the 7th power times 5 to the 4th power times 9 to the 3rd power divided by 6 to the 5th power times 10 to the 3rd power. Now that's something we could do mod 11, but it would be a little bit taxing. It's easier to move from this world into this easier world and then move back again. So we're going to find the log of all this. So we're going to write the log of all that. Now, when we find the log of 3 to the 7th, it's actually equal to 7 times the log of 3. And the log of 3 just takes you from here to here. It's a function that takes this input, gives you that output. But this becomes 7 times the log of 3. And the times becomes plus, because over here where we're multiplying, over here we're adding. So it's 4 times the log of 5. And we're going to add 3 times the log of 9. And we're going to subtract instead of divide. Subtract 5 times the log of 6. And we're going to subtract 3 times the log of 10. Okay, so the log of 3 is 2. So it's just 7 times 2. Plus the log of 5 is 6. So it's 4 times 6. Here I'm going to go 3 times the log of 9. The log of 9 is 4, so it's 3 times 4. And then I'm going to subtract 5 times the log of 6. The log of 6 is 1, so it's going to be 5. I'm going to subtract 5 times 1. And finally, I'm going to subtract 3 times the log of 10. The log of 10 is 5, so I'm going to subtract 3 times 5. So I get this. I'm going to simplify that down below. So 7 times 4 is 14, which is just 4. 24 is 4 again. Plus 2, 12 becomes 2. Minus 5. And minus 15 is 5, so minus 5. So that's 4 plus 4 plus 2 is 10, which is equal to 0. Minus 10, all this is 0. The anti-log of 0 is 1. So we got 0 over here. When we move over here, it becomes 1. So the answer to all this is 1. And we don't have to do all that hard work. But just because we don't have to doesn't mean we're not. We're going to do all this hard work to make sure we got the right answer. First, we start with 3 to the 7th power, which is 3 times 3 times 3 times 3 times 3 times 3 times 3, which is 9 times 9 times 9 times 3, which is 81 times 27. 81 minus 77 is 4, and 27 minus 22 is 5. And 4 times 5 is 20. Take away 11 is 9. So we're just going to write 9 here. now we're going to work on 5 to the 4th power, which is 5 times 5 times 5 times 5. So that's 25 times 25. 25 minus 22 is 3, times 3 is 9. So we get another 9. Now let's work on 9 to the 3rd power. So that's 9 times 9 times 9. That's 81 times 9. Subtract 77, you get 4 times 9. That's 36 minus 33 is 3. So this is equal to 3. And then we're going to divide by 6 to the 5th power, which is 6 times 6 times 6 times 6 times 6. 36, 36, and 6. 36 minus 33 is 3, times 3 times 6. That's 9 times 6. That's 54, minus 44 is 10. So 6 to the 5th power is 10. And finally, we're going to go 10 to the 3rd power. Well, 10 times 10 times 10 is going to be 1 times 10. And 1 times 10 is 10. 10 times 10 is 1. So we're going to get something over 1. 81 minus 77 is 4. 4 times 3 is 12. Take away 11 is 1. So we get 1 over 1, which is 1. Okay, so over here we got 0. The anti-log of 0 is 1. So we expected to get 1, and we did get 1. But doing this multiplication was more trouble than moving over to here where we're adding. So, but the value here is not to get an answer. The value here is to understand logarithms. So to extend this lesson, we can make new problems. For example, you might say, whenever you add these two numbers, mod 10, that you're going to increase that sum by 2. So you could write s plus 2. So for example, if this was 1 and 2, instead of writing 3, you'd write 5. Whatever the sum is, you would increase. So then you want to add the numbers. You still want to work with the numbers 0 through 9, but you want this number to be 2 more than the sum here. So if you do that, that gives you a new problem to solve, and you can use algebra. To start with, you could still have 0 at the top, but now you could also have 0 down here. And you could start with C, B, and A. And you go through the whole algebraic process, which we won't do. And it turns out this will have a solution. And this problem will also have a solution if you put 0 at the top. So you can, I won't demonstrate all the work, but if you followed the first part of the lesson, you can do this for yourself and do this with your students.